I think we can start. So today we will host here the 6th international lecture and conference of the European project PRELUDE. That is speaking in this specific case about intelligent building, digital twins, platforms, data treatment, lesson learned, BIM, smart building in general. Okay. Where we are in a series of lectures and conferences which are organized and supported inside the European project PRELUDE, so funded by the European Union. That has as topic the communication, the dissemination, and especially opening debates for what it is possible with the audience about topics correlated to smart building operation, low energy building, climate correlated buildings, and all the aspects that we treat with a lot of very interesting partners inside this project. We already had 5 conferences before, from 2023 to now, and we still have one planned for the 14th of June about climate resilience. Okay, with that we will arrive to the final event that will be in October, November for the educational season. They are what? Speakers are recognized experts. They come from university, they come from companies, they come from research center. They are correlated to the architecture and engineering world. Who attend this cyber conference? Students, university students mainly, professional, because we had several of them, especially in learning, and open to interesting. That's clearly the topic of the approach. Only a short recap before starting. No? This is inside this PRELUDE project that is prescient building operation utilizing real-time data for energy dynamic optimization. Now, the title gives a lot of idea what we are speaking about. It's quite complex, okay? So the topic is clearly supporting, developing, testing, okay? Innovative, low cost for what it is possible, and smart solution for intelligent building and future building control approaches based on proactive services. So it's not only I control a building with threshold. It's not only I control a building with a general machine learning that optimize what to do today. Is I control a building considering how the building will react if today I do that and tomorrow what I choose today has an implication. Okay, because we all know as architect, the majority of people here is architect, that clearly the implication of building control is not only something that arrives one second, especially in the thermal point of view. We have thermal masses, we have the activation, we have the proactive control logic and the maintenance logic of the system and so on. These things need to be controlled. So the scope is minimizing energy uses, maximizing for what it is possible self-consumption and using of renewable sources at site level, okay, and especially improve comfort condition for what it is possible using the free running potential for what it is not possible using low energy consumption in general. The project is developed on a modular platform. We will speak also about that today, okay, which is hosted and supported by the middleware solution POSIX. And several modules has been developed inside the project and has been connected to that. Because one of the other big issues in smart building is intra-data connection, multiple platforms. We do not have one provider. We have multi-provider, but how to manage these things, that's a very open issue. So a short recap, what we are speaking about. PRELUDE has a lot of partners, okay? We have more than 20, let's give an idea, from all around Europe. Okay, we have demo cases in Denmark, Italy, Poland, Switzerland, and Greece. And we also have a very advanced living lab inside the project in Austria. Okay, an incredible smart building, even very, very complex. And what we test on that? We check integration inside one platform. We check dynamic free running potential. We check indoor-outdoor correlation, weather prediction, temperature and consumption prediction at different levels. Okay. We have occupancy profiles. We have the possibility to support predictive maintenance. We will see something today on that. We have the possibility to support and manage comfort and energy efficiency optimizer. And again, we speak about that today. And we have the possibility to support a lot of other things, measurement verification, renovation roadmap, and so on. Okay, you can imagine the largeness of the approach. as you see by the map, partner cover the majority of Europe, okay? And also the demo cases as it. So today we will speak about PRELUDE, which is the middleware of the project, which is a project that supports this PRELUDE. It's based on the PRELUDE portal developed by EMTECH, will be presented today. And the logic and what will be presented is about really the complexity of managing a lot of data and preparing the data for building control. That's not simple, I can say. The second things, we have a presentation by Lorenzo Farina and all the supporting by STAM, which is an Italian-based company. Okay, EMTECH is a Greece and Germany-based company. I think the Vagelis will present better than me. Thank you to be there. And the STAM will present its logic, its model, you can say, an experience on developing a comfort energy efficiency and maintenance module that integrate year a lot of data and aspects, okay, and also involve people in some way because of the graphical user interface. And after that, we will have the presentation from Rosaria Groups, that again is an Italian-based company with a lot of potential sites, okay, around Italy, but they will present again better than me what they do. That's very interesting, especially for architects also in the room, because it connects not only comfort efficiency and but also the model. So BIM, advanced techniques for model the buildings, predictive maintenance. That don't be scared as future architects in the room. The maintenance is a big and large working topic, okay? Because the buildings are there and we need to maintain the building. Especially in Italy, actually, but also South of Europe and part of Europe, okay? So that's really a big market to be considered, not leave behind. So that's roughly speaking what we will see. So all the international experts and organizers today come from the company domain. That's also very, very important because we need to have innovation and innovation on the market. So that's our program. I already presented what we will do. So I will skip this part and leave the floor to the presenter. Before leaving the floor to Vagelis from EMTECH, I will only remind that this educational event series is part of a large educational action inside the project that involves, on the one side, as involved in 4 years now, we have a long project. Students from engineering, especially some architectural students that are developing smart building and IoT connected solution like this smart weather station or multi-comfort elements. It's not a bomb, okay? It's a sensor with cloud connection, IoT, and a lot of other solutions like that one. We have more than 9 now, so it's quite interesting. And in addition to that, we also have a citizen science approach, and now it's going in School of Piedmont regions with some problems in collective sensor because the time for producing is long, but we still have 3 schools working, another 3 ongoing, so more than 800 students throughout for indoor quality and indoor environmental quality measurement and use of the measure. That's where we are. And so thank you very much to all of the speakers and to all of the people here present. I hope that you want to do questions, okay? You can use the chat. You can also in some way, not in the middle of the presentation, please, but when you have time to ask for that, that will be very, very well. Don't lose the opportunity for that. Okay, so Vagelis, I think that is your turn.
Hello, good morning from my side. Okay, so good morning again. As Giacomo said, I'm Vagelis. I represent EMTECH. EMTECH is a company that has 3 separate offices in Greece, in Germany, and in Cyprus. And the company has different domains. And let's say the most important ones are the space domain, the smart grids, smart energy grids, and smart buildings. So with that in mind, I will be examining the PRELUDE, let's say, project from a software standpoint, as we are responsible for providing the middleware for the solution. So starting off, let's say, as I said, from a software perspective, what we have to do here. So again, as Giacomo said in his introduction, we have different partners with a high level of expertise that provide intelligent solutions to improve building performance. So these technology providers basically require monitor data from the building itself. They do some operation and firstly provide control to the building, if possible, of course, and secondly, provide additional information to the tenants and other stakeholders of the building. So this is the, let's say, the idealized case of what we have to deal with. Now let's see the reality. So the clear concept is more like this. And here is where the problem starts. So the different technology providers actually are not independent. They're interdependent, meaning that outputs from one technology become part of another technology, because imagine that you want to do some proactive control on a building, then you need some sort of forecasting algorithm output that is provided from a different technology provider. So these two need to communicate among them in order to provide a solution. Also, of course, we do not have one building. Alone in the PRELUDE project, we have 7 different pilot buildings. And in the general case, of course, we have unlimited. And that's okay in general, but in the specific case, from a software standpoint, you have to consider how each building provides its monitor data to the different technologies. Different buildings have different monitoring solutions. In fact, they may even have more than one. So different solution for indoor air quality measurements, different solution for weather monitoring, different solution for energy consumption. So this creates the problem to the technology provider that they need to accommodate everything. So every different protocol, every different communication mean, additional programming and software needs to be written for historic information if needed in their environment. And this creates a lot of, let's say, software engineering overhead to a technology provider who is an expert in specific and highly technical things. And in this case, they need additional people, software engineers, to do bridges, handle security, handle scalability, and handle things that are in general not suited for their domain. So this is in general what a middleware does, and this is what we provide. The middleware, as shown by the name itself, basically sits in the middle of everything. So all of the buildings provide their data to the middleware. All of the technology providers take data from the middleware only. And if they have control to provide to the building, they give that again to the middleware, which is again responsible to provide to the building. This is the general concept. So this means basically that the middleware is responsible for handling all of the communication interfaces, the data handling, and so on. And the technology providers only need to concern themselves with a single entry point, which is the middleware only. And it is irrelevant then how many buildings you have or what kind of communications means and monitoring systems each building provides. So since the middleware is in a position to do that, it also provides typically some generic, in some sense, services that are useful typically to technology providers or even buildings. And this includes analytics. It handles databases in order to provide historic analysis, historic data, and so on. It handles user management in the sense of handling permissions of who can see what type of data and why. It also handles multiple users and controls in general the whole performance of the application. So basically, middleware is a streamlining component that we use in order to make our lives easier when we want to do higher level technical functions. So in order to do that, EMTECH has developed and is providing in the context of PRELUDE the physics framework. This was initially designed as a decision support system back in 2013, and basically imagine that physics at a very high level and perhaps a bit simplistically is, let's say, a software library. And what it does, it provides a series of features that allows us to build applications quickly. So the framework, first of all, provides abstraction visualization of data resources. And this is super important and the core of why we use it. So what this means is basically that, okay, data comes into the framework, that's fine, but within the framework, they follow a very specific schema, which we call an information model, and this defines how we can traverse, find, and use the data that we have. This is the concept of abstraction and visualization. Of course, it can be deployed on any type of architecture, either cloud or server, and this can be used to enhance scalability when needed. It can provide simulation support since it has built-in bridges for various tools such as MATLAB, Scilab, Octave, and so on. And it enables the creation also of user interfaces by providing a low-level programming interface to make it easy to write user interfaces using a specified schema for all of the data that are available. So now using this framework, we develop applications which, as I said, collect data from different sources, regardless of what they are. They abstract the data in a common language that can be used within the application. And then, of course, processing follows and reporting of the final elements to the end users. So let's see now how we build the physics application, which is what we did for the PRELUDE project. Physics is basically comprised of 4 elements. The first is agents, which imagine that are simple standalone programs that only use the services provided by the framework itself. Then we have the information model, which, as I said, defines all of the inputs and outputs of the application. And this is how agents interact. Also abstracts the agents, meaning that it is not necessary for agents to know where the data come from, in what format they come in, and so on. So they just say, for example, that I need a temperature range with this granularity and for this time period. And if you give me this temperature range, I will give you back a prediction that is 24 hours ahead per hour. And that's it. Now, where this temperature comes from, if it comes from various places and so on, it's irrelevant to the agents. Now, agents are collected in nodes, which are basically, let's say, containers that we can deploy easily in order to scale our application. And physics also provide a set of services that are common to be used among agents and provide common functionality such as logging, scheduling, execution of agents. So we can say, for example, that we want to run something every day or every 5 minutes in order to perform a function. And this is the general idea. So how do we use all of these things? The first thing that we do optimally when we design a new physics application is to define the information model and basically say what data comes in, how it is transformed, how it is propagated through the application. Having done that, we can generate the agent code automatically using physics tools that we have developed in-house. So basically, we have an empty programmable block that has all of the necessary connections ready, and all of the only thing the programmer needs to do is implement the specific logic of the specific agent, which is also the third step. And then, having done that, we just arrange our agents in nodes or containers, and we deploy wherever is necessary to run our application. Physics in Prelude is used in two different ways. We provide the Prelude Middleware, which, as I said, is the central component of the interaction among the Prelude partners, and the PRELUDE Portal, which is a visualization element that allows external users to interact with the data that we have collected within physics. This image here gives a different view. It shows the centrality of the physics middleware, and we can see that here that all of the buildings are on the left-hand side of the diagram. Then we have a series of technology providers that provide different aspects of control, monitoring, and in general optimization of the building's performance. And everything talks and interacts with one another via the middleware, which is a physics application. So this is, let's say, the general high-level view. Now, if we want to quickly see what the whole process is, firstly, we start with the monitor data from the different buildings, since we consider those to be the lowest level of information that we have available. So this is the part of data collection. Then we have a stage which is data pre-processing, which basically means that we check the input data for any issues and we report them. For example, there may be data gaps, there may be outliers, there may be anything that seems out of the ordinary is filtered and optimally fixed at this stage. As an additional step, we perform data aggregation within the middleware. So since we have different buildings, different monitoring plans, what happens is that data come in an unorderly fashion, let's say. So building A could give us temperature data every minute, and another building can give us temperature data every 30 minutes. So this can cause confusion, and this can also hinder certain technologies. So what data aggregation simply does is summarize data either on a temporal manner. So saying, for example, I want the average of every 1 hour for every data input stream that I have, and can also aggregate data on a special manner, so that we can say that I want to see the energy consumption of the whole building. And this needs then to average or collect, let's better say, the different energy measurement sensors that I have throughout the building and give a single value. So temporal and spatial aggregation are also provided. All of the data produced, both the raw data from the data collection and the aggregated values, are then stored and handled with appropriate databases, which are also controlled for privacy, access, and so on. And then we move to providing all of this data, either produced or collected, to the different technology providers to use as they see fit, and return the results back to us to either interact with the buildings or visualize to the different shareholders that we have. Moving forward, this gives a level overview of how physics is built on at a high level. The first component that we notice here are the bridges. And what a bridge do is basically a simple agent that collects data from an external source, regardless of the protocol or method of communication that this source has, and transforms this input into a cohesive information block as defined from the information model of the application, which, as I said earlier, is critical to a physics application. Then we have anything that has to do with data management, as I said, data aggregation, data pre-processing, and so on. This belongs here. And we have data storage, which, of course, controls storage to databases, both storing and retrieving. And if we want to allow external elements to interact with physics in order to get data from it, we provide a series of APIs that can be used from any stakeholder that is involved within the project. And finally, all of the information is shown to an appropriate user interface. Now, moving forward to the next part, this is the PRELUDE portal, which is basically visualization of physics data, taking into account two different user types, the one being the tenant of a building, and the other being some sort of expert, either building manager, engineer, and so on. The differentiation here happens because we want to visualize differently to different people, since they have either expected different technical capacity or they are interested in different things. And this PRELUDE portal, of course, is aimed to support every building that is included in the PRELUDE project as a pilot case. So the general structure here is that we have 4 main pages, which is the login, of course, dashboard, real-time analysis, and an event log. And the actual content of these pages depends on the type of user that is connected to the application. The portal is currently a work in progress. It's being developed as we move closer to the project closure. And just to give a rough overview of what we can do here. So the goal of the dashboard is to allow users to see at a glance what is happening on their space. Here we see a tenant view, so we can quickly see, in general, the last 24 hours of, firstly, the indoor conditions of different rooms, the general electrical consumption of the apartment, thermal consumption, and also upcoming actions that are generated through the different modules of the technology providers. So if there is an action to open ventilation or do some action like so, it will be shown on the upcoming actions for the user to quickly know what needs to be done. Then we go to the events, which is basically an analytical view of all the action and events generated from a specific apartment in this case. So the user can see either a filter either by severity of the event, select the specific room that we want to examine, for example, living room, corridor, and so on. And of course, select the range of the events to be shown. Then we have the historic data view, which is here we can see the raw data of every sensor that the user has access to. We can filter here by room and by sensor, and we can select any data range that we want and examine then for any abnormal behavior visually. This also shows, of course, appropriate threshold for the different sensors available, and all of the data can also be exported in various formats for further use. And this is basically the PRELUDE portal at a very quick glance. And let's say, before closing, I want to elaborate a bit on how we view PRELUDE within EMTECH. So PRELUDE has, of course, led to a better understanding of sustainability, energy efficiency, and comfort optimization problems, and how this can be resolved and handled on a building environment. And with that inspiration, we started developing our own monitoring solution, which includes both hardware and software, which is targeted at school units to monitor and improve classroom indoor conditions while also considering an energy efficiency approach. And we call this solution simply Comfort. Now here, the idea is that we want to do two things. Firstly, improve classroom environmental condition, and secondly, and perhaps more importantly, is to educate students in the different aspects of energy efficiency, comfort, the impact of environmental effects on our health, and so on. So for the classroom environmental conditions, we provide continuous monitoring and AI processing, and based on that processing, we give recommendation to teachers, principals, and so on in order to better handle their building. And in order to support the education aspect of Comfort, we have developed a chatbot that allows interaction between students and teachers, a series of seminars, and appropriate training material to support this educational journey. And if we want to see the technology at a glance, basically, within the company, we develop both the hardware and the software, so we are completely vertical in that regard. So we develop our own sensors, which are installed in every classroom, and they measure temperature, humidity, luminance, and carbon dioxide. And these sensors communicate with a central gateway device, which is edge-enabled, meaning that it has a strong enough processor to do all of the needed processing on the spot without needing to communicate with cloud services and so on. So basically, the gateway collects all the data of the sensors, perform calculations, and provide recommendations to teachers and principals in real time. And in the meantime, a dashboard is also provided in order to visualize all of the information and show how the comfort system operates within a school unit to different stakeholders. I think that's all for me. Thank you for your attention. If you have any questions, please feel free to ask me.
Thank you. Do you have an immediate question? Otherwise, keep question for the end. Okay. Thank you. So now, your turn.
Buongiorno a tutti. Hello, everyone. I am Marco Barbagelata. I'm not Mattia Repossi. Unfortunately, he's much taller than me and better looking. I am his boss. And today I will actually just take care of introducing the role of STAM in the PRELUDE project. I think Giacomo, the Professor Chiesa, did a great job in introducing the project. And then Lorenzo will describe one of the key tools that we have developed and have been developed in the project, which is what we call the comfort optimizer. Because reducing energy, if you take it just as a simple problem, it's very simple. Just turn off anything that consumes energy. The thing is, we need the energy to do stuff. And the stuff we do and the way we do it is something that affects the comfort of the building, intended in a kind of wide spectrum. So the idea is, I'll take you through a quick, I promise, very quick company presentation so that you get the picture on who we are and why we're here talking to you guys. Our energy platform, actually, I will leave most of that to Lorenzo. And then we will get into detail on what we've been doing in the PRELUDE project and how we've been doing it and the results that we had so far. So very quickly, okay, well, I hope you're smart enough and awake enough to figure out that 7.5 is not that we are 7.5 people, but STAM is a company that does tech consulting. That means we are consultants, but unlike most consultants, the output of our work is not PowerPoint slides. As you can see, this is not our strong suit. But most of the time it's technology, mostly software, running software, automation solutions such as robotic cells, whatever, simulation models, and complex system design, so prototypes of very complex systems. We have been working for a while. The company was founded in 1997. I assume it's older than most of you here today. The average age in the company is 33, which for you is probably crazy, but it's a pretty low age for a company of 75 people. We have a turnover of about 8 million. When PRELUDE started, we were joking earlier, it was around 3, so we had a pretty exponential growth over these years. And to prove that I'm not a liar, that we're actually a tech company, we also have patents, so we protect the intellectual property of the technology we produce. And last but definitely not least, we are one of the top companies, private companies, playing in this field of European research-funded projects. I think we are #1 among the small medium enterprise and among the top 10 in any company, basically. Our main office is in Genova. You would probably hear it if I were speaking Italian, because I have a pretty Genovese accent. We also have an office in Rome, one in Cagliari that has been working very actively on the PRELUDE project, and one in Bari. Nothing in Turin yet. Hopefully this could be a first step to actually move here. We are organized around what we call business areas. Each business area to us is, let's call it practice. Meaning if you point your finger at one of those business areas, you figure out pretty much what the people inside can do. So you got the robotics and mechatronics business area, which does robotics and mechatronics. So most of robotics guy, mechatronic guys developing automation solution and robotic solutions. Then there's the nerds, us, digital solutions guys. So we do the software mostly for different domains, but it's mostly divided into the so-called product owners that take care of designing the software and the complex solutions, and the developers that actually implement solutions. We have a team devoted to energy and sustainability, one devoted to research and innovation services, and one that is focused on engineering solution, mostly for the aerospace domain. I will not bore you with all of that. Among the digital solutions, what we do is we do software engineering, meaning we figure out how to do complex stuff that doesn't exist with software. I underline that doesn't exist. We are not a software house, so we do not have a product that I would just try to sell. People come to us with a challenge, and we try to solve it with a technology. We have what we call integrated asset management platforms. So basically platforms that take care of models of the infrastructure. So I was seeing, a CAD model on your PC. We take complex version of that Rosaria will present all about that. And we try to match it with real data, time series, to figure out how the infrastructure, how the asset is operating, how it's working, based on information in the model and based on the real-time data that we get. We also have energy management systems, both standards energy management systems, if they exist, and non-standards, meaning that we try to figure out how to operate efficiently, not just reducing the consumption, but moving the consumption of energy over time so that it's beneficial to the network. And then last but not least, we have what we call an ecosystem management platform. Not interesting for you, so forget about that. About our energy management solution, we have what we call the so-called Empower platform, which was my dream in 2018, and it's close to reality now. And it focuses on the different layers of the different phases of operation of an asset, whatever asset, building, an industrial facility, whatever. So it goes from the design phase, where we have simulation tools to enable optimal design, most of the time interacting with BIM models. We take care of the operations through energy monitoring and management, predictive maintenance, and what we call the energy optimizer, which Lorenzo will make much more concrete in a second. And this is, of course, all based on what we call the data retriever. So how do we get the information about the asset? How do we get the information about what the asset is doing and how it's behaving? And with this, I will probably give it to you. Thank you all, guys.
So, as Marco said, our approach is to empower the user. So, help him or her to make the best decision possible. So, this is the case of the operational point of view. As already said, we have, let's say, build our development, our platform on the optimization, so mathematical formulation of what is the system, how it is behaving, and also how to optimally control it. Control it in, let's say, in a higher level in 2/3, let's say, point of view. One is the indoor comfort, which is sort of against the energy efficiency, as already said on this day. Indoor comfort can be at different levels, for example, the thermal comfort, the acoustic comfort, but also the lighting, the illumination. We focus our attention on the thermal comfort because it's the most energetic one, so it's the most interesting to optimize. The energy efficiency, so the way of telling supporting the user to reduce the consumption as much as possible, or also move it when the energy prices are low, and also move it when the renewables are more producing. Because as you probably know, the renewables, when they are producing for free, so you don't pay any fuel, for example, for the PV or wind turbine. So it's the objective is to use this power, this energy as much as possible. On the right, you see an example of our platform, in a sense that this is the result page. So it's an example in which we try to nudge to help the user to make the best decision in terms of, for example, a KPI, which is the cost. Telling for example, the user that if you behave like this, if you plan your activity, your energy consumption, the sort of way that you, for example, can save this amount of money, can help a lot in making this action true. And also other graphs about the thermal comfort that is leading to this action, and also the actual consumption. So this is the approach for energy optimizer. Looking at the other technology, so the predictive maintenance, which we developed together with Rosaria in the PRELUDE project. This is like an introduction, because we have different type of maintenance, approaches. And the first one is the reactive maintenance, meaning that for a machine, a general machine, the health, the status is decreasing with time. So the reactive maintenance is basically waiting for the failure to actually then provide the maintenance. Then there is another approach, which is the preventive one, which is basically what we are mostly doing also with our cars and vehicles. That at scheduled time, we basically provide maintenance, so a fixed amount of time, disregarding of what is the machine status, machine health in this case. Then there is the new approach, the more innovative one, which is the predictive maintenance. In this case, the machine health is somehow estimated using data, using algorithm, whatever, but somehow it's estimated in a sense that it's also possible to predict how is the machine behaving in the future. By predicting this status, is also possible to predict when the machine is going to fail. And by knowing this, the objective is to plan the maintenance just before this failure. It's a very complex task activity, but it also leads to many advantages. For example, it minimizes the unplanned downtime, so when the machine cannot work because it's in maintenance. It reduces the operational costs in general, and also it provides alerts for unexpected problems. So it gives the alert to the user in near real time. So this is our approach on the predictive maintenance. As we are good at software, we started with the data source. We gathered the data about a general machine. In case of PRELUDE, we focus our attention on the HVAC system and PV also system in some cases, because they are the more let's say important assets in some way. So we gather the data. We use an interface to, let's say, a platform to orchestrate this data, and then we train the anomaly detection model. So our approach is based on anomaly detection, meaning that using these models on real-time or near real-time data, we can estimate how many or how big are these anomalies on the data. And then our approach is also to use the user feedback, because the anomalies that are given by the models are just based on the data. So it's also important to have more real, another feedback from the user. And by, let's say, merging these two information, we, let's say, we output an indicator that we call anomaly level, which you see let's say, an example on the right, in which is basically a proxy of the machine health that you saw before. So, for example, if the anomaly level along different time is increasing, it means that machine health is decreasing. So it's important. It's an important indicator to show, to also predict how would be the machine health in the future, so that the maintenance can be properly organized. As previously mentioned, here are some examples of the application of this technology in Prelude. The first one is in the Living Lab Energetico, which is an office building, very advanced building in Austria, in Pinkerfeld. As you can see, there are different technologies. For example, the PV system, activated thermal masses. Then there are also heat pumps and ground heat exchanger. Moreover, there are many sensors placed in this building, so that we could retrieve this data and perform our analysis and our developments. From the energy optimizer point of view, we firstly had a modeling task, which basically, for the optimization to work, we had to characterize as much as possible the internal behavior of the system. We developed this model that we call ARC model, because it's based on 3 different parameters, alpha, R, and C, which are, let's say, physical quantities. So alpha is related to the sun irradiation, R is related to the thermal resistance of the building, and C is about the thermal capacitance of the system. Our approach to actually use the data to develop this model is a so-called gray box. Gray box means that using physical interaction, physical equation, let's say, we then estimate the parameters of this model by using data. So it's like a mixed approach, both from the physical point of view and also from statistical and data point of view. So by knowing the variables that you see, I don't want to go too much into details, for a long period of time, we were able to estimate these 3 parameters in order to minimize the difference between the predicted internal temperature and the measured one. As you can see on the right, this is an example on the Living Lab, which on the top you see that internal predicted and internal real about the temperature are quite close and following a little bit the behavior. From the other point of view, the predictive maintenance, we also use the data coming from the Living Lab to firstly perform our models. In this case, we use the data from a simulation room. I mean, it's a real room, but here you can see the sketch. It's an office room, and we focus our attention on the air handling unit, AHU. So by using 4 years of data, we firstly train the models and then test them. The models are, in general terms, clustering models, meaning that the objective of the model is to group the data in a space as much as possible. And those data that, let's say, are outside of the cluster or even, say, distant from it, they are categorized as anomalies. So as you can see on the right, we use this data to plot also them and see how they perform. And you can see that in red and purple, there are the anomalies that are quite far from the actual normal operation that it's great. Then the second step that we perform is to validate the 2 models, the 2 tools, on another case, which is this pilot, which is in Denmark. It's a single-family house that also has quite a few high-tech assets. For example, PV system, heat pumps, and also new entries, also an electric car, which was bought by the tenants, which are a real family. Moreover, there are some quite few sensors placed in the house. So from the energy optimizer point of view, we want to validate this model as much as possible. As you can see on the top, we try to perform different, let's say, tuning of this model because the data were different. So we had to, let's say, check more what to do. We use the internal temperature as just the living room temperature at the first. Then we wanted to have it more complex. So we also have the irradiation data and also the blinds, the shutters opening and close data. Then we use a proxy calculation for the HVAC system to have more accurate estimation of what is the input, the heat gain, by using the air flow rate and the temperatures. And then we use, at the end, we want to have it more accurate to have by having the temperature as the weighted average of all the monitored rooms. Unfortunately, we didn't succeed. So after all these 4 steps, we didn't have a quite good accuracy in predicting the temperatures. So at the end, we wanted to test another approach, which is fully black box. Black box meaning that is fully statistical, not let's say mostly disregarding about what is the physics. And there are many statistical models. In this case, we use a neural network. At first, we had very promising results because also the neural network can be flexible, so you can enlarge this network as much as you want, but with the limitation of how many data do you have. Because if you have more data, you can have more complex model, but otherwise, it's better to have less complex model. So there is a disadvantage of using black box models because you cannot interpret. You have low interpretability on the output. You have predictions, but you don't know why there is this prediction, and that's why it's called black box because you cannot see inside. And also in our case, we didn't have time dependency between the variables, which is actually in reality true because, for example, the irradiation at 1 hour can also lead to a higher temperature on the next hour and so on. But we are let's say confident and hopeful that we can succeed on this and develop, say, a better move. Lastly, we want to also validate the anomaly detection model. So we firstly connect the platform with the and train different models, and we use physics data. And we actually were very lucky. We were the only one happy that the air handling unit was broken in 2022. So we had a real failure to be tested. So these are the data that we use: the power consumption, the airflow supply, and the airflow supply temperature. And we basically, as you can see on the right on the timeline, we trained the model just before the failure of the air handling unit. And we wanted to test the anomaly detection, how it performed on both the broken and also, let's say, adjusted the air handling unit. As you can see on the plot, we have quite high anomaly count for the broken part, and also quite few anomaly count on the adjusted one. So on in this case, we were actually happy on this test. But it's a first test, and we can work on more. And that's it from my side. These are our contacts. If you have any questions, I'm here.
Yes, well, we have one question.
Is the model being provided adaptable also for various scales for schooling for residential processes?
You mean the predictive maintenance or the platform? The energy optimizer? The whole. Well, we are actually more specific for residential. So, for example, the model for the anomaly detection model is just specific for a single asset. So, meaning it's also flexible on the type of data that you can input to them. But yes, it's very specific to residential case. In this case, for the optimizer, instead, the data were, let's say, more on residential scale, office, not multiple offices, just one. Because one, let's say, limit that we saw is that the energy optimizer is working on a single thermal zone. So if you input multiple thermal zones, for example, like in the pilot, in the Danish pilot, it didn't perform so well. So there are some complexities inside that are not well modeled yet.
Nice to meet you. Of course, I'm not Rosaria Aversa. Rosaria Aversa is she. So I'm Amilcare Paolella, the responsible of the Chief Innovation Officer in La SIA, mainly responsible for research and development in La SIA. La SIA is an engineering company, and what we do nowadays, engineering and also architecting company. Thanks, Alessandra. Alessandra Speranza is our general manager in La SIA, so our boss. So what we do in La SIA, mainly we talk about civil and design field. We work in the civil design field, but also in mobility infrastructure, telco, and of course energy. And in parallel, we also provide advisory services like project management, work management, expertise in exploitation events like this. So with the academy, with the university. Of course, as an engineering company, we are a tech company, so based on technology company, and we provide, say, expertise in BIM, scan to BIM, digital twin, so all these kind of things that are really important in this moment. And just because we are a technology-driven company, we use advanced technology tools like drones, like scanner, and we use those kind of tools also in projects like PRELUDE. Rosaria will explain to you the details about what we did in PRELUDE, but more what we complementary do outside PRELUDE, just to let you understand that it's not only an exercise in the university, but it's also something that comes in the reality. So I will give the floor to Rosaria. Thank you.
Thank you, Amilcare. Good morning, everyone. It's a pleasure to be here. So my name is Rosaria Aversa. As Amilcare said, I am an architect. And as Lorenzo said before, in PRELUDE project, we dealt with the predictive maintenance module, and we developed the user interface platform related to the anomaly detection algorithm. But talking about data treatment and platform, today we want to talk about also the role of BIM in this kind of process. So we know that BIM is about the digitalization of all the geometric part and also, and most importantly, of all the information that we have inside the model. And this is very important to monitor all the phases of a construction building. So from design, construction, and most importantly, maintenance. So we want to share our experience in this field. We developed a platform called the AM platform, such as asset information management. And this platform was born with a telecommunication project, but now we apply it in the civil engineering. So the AM platform is able to load and view multiple models, and most importantly, allows the managing and the monitoring of all the data that the model has inside. So which kind of data we have? We have static data coming from the model itself, like Marco was saying before, and we have also dynamic data coming from some IoT sensors physically placed inside the building. So here there is an interface of the platform, and as you can see, we have many models on the map, since the models are geolocalized, and the models are in an open file format, so you don't need any software to check the platform, except of course the platform itself. Once a model is loaded in the platform automatically performs a real validation of the model in terms to check if all the information that we made in the BIM model are readable. Then we can have more versions of the model, because as you know, the model can change during time. So the platform allows to have many versions of the model. And also you can update documents that you need on the platform. Selecting, and then we are going to see a video of the platform. Selecting a site, you pick a site from the map, you can preview the model, and also you can see in the middle here, you can also see the general information. So when you open a model on the platform, as you can see, we have federated models. So we have the architectural part, we have the structural part, and of course the systems. And selecting each element, you can see all the information contained in that element. But how we manage this information, as you can imagine, we have a lot of information. So here comes in our help the customized dashboards that sort the information depending on the user's needs. So what do I need to know? I can filter this information and have what do I need. For example, here, and we are going to see in details later, we can have an overview and also some details. And in the bottom side, we have the dynamic data that I was talking about before. So what is the use and who are the users of the platform? So the use, of course, is related to maintenance, because if I can control this kind of data during the life cycle of a building, I can save costs and, of course, time. But who are the users? So the platform was designed, and we did that jointly with STAM, to be used by anyone. I mean, you don't need to be a BIM expert to use the platform. So, for example, a maintenance user can check the platform and can check the information by their tablet or the smartphone, and also update the information. Okay. Okay. Here we have a video of the platform. For example, I pick a site from the map. In this case, we have an historical building called Palazzo Santa Caterina, and the owner of this building is the Italian authority Agenzia del Demanio. And as you can see, after picking the model from the map, I can navigate the model, and I can also measure the model, because as you can see from these tools on the bottom, I can do many things, and I can also take measures from the model. Here you see the architectural part, the structural part, and it is possible to see all the layers that the model has inside it. In fact, as you can see, if I turn off and I turn on some layers, I can see what is behind. For example, here we are going to focus on the firefighting systems. I pick an element and I can see the information that I have inside. So, for example, I want to know the maintenance interpretation, or which is the state of maintenance for my firefighting system. How do I do? I go, as I was saying before, to the dashboard side. We are coming in a minute. Okay, I go to the dashboard side. From the pie graph, I can see which are the elements of my asset. So all the elements of the firefighting system. In the middle, I can see which are the elements who need to be maintained. So I can schedule and program the maintenance intervention. And also I can have the historical of all the intervention I already did. So the elements that were already maintained. As I was saying before, here we have the air care monitoring part. So setting some rules that you can see we are doing in this moment. I can have information in real time, or for example, in the last 30 days about the air care monitoring. These, of course, are connected to IoT sensors placed inside the building. So the next step that what we want to do next is, of course, match what we did in Prelude and that Lorenzo explained before, so about the predictive maintenance module, to match it with the AM platform that I was explained. So also have a correlation with BIM and predictive maintenance through the platform. So, but how a model can be read from the platform? Everything goes through the coding rules. It's essential to set some ground rules that are some codings that can be read from the platform. So this is about platform and BIM, but which is the BIM process? In order to explain how a model is born, we would like to talk to you about today a real case study, a model that we carried out last year, and it's a very complex structure that might be interesting for you. The case study is the city of sport located in Rome, better known in Italy as the Vela di Calatrava, and it was designed by Santiago Calatrava architect for the Swimming World Cup in 2009. Unfortunately, this structure was never completed. So
too complex to be finished.
Yeah, it was too complex, and also due financial problems, it was never completed. And it's one of the biggest unfinished work we have in Italy. So the owner, which is Agenzia del Demanio, again, asked to La SIA to do some service about it. And to give you a photograph of the complexity of the structure, we have almost 500,000 square meters of the outside area. The iconic cover is more than 60 meters high and has more than 6,000 connections. What Agenzia del Demanio asked, we carried out the scan to bin survey of the whole area, documentary research, structural investigation, and of course, maintenance plan. So, which is the first phase? The first phase is to set some building modeling, specification. So, which is our goal? Our goal, we need to set which is the information level that we need. We have to standardize everything through centralized templates, shared parameters that can be read from the platform, and of course, associate the codes to the maintenance plan. So phase 2 is the geometric acquisition, how we carried out this kind of survey. First of all, to make the survey of such a complex structure, you have to plan the survey. You have to design the survey to assure that the whole structure is covered. In this case, we use three tech tools, laser scanner from the ground, and here more than 1,000 stations were performed. Then we use drone to make the survey of the whole area, and then ground control point to match the laser scanner and the drone. So after the survey is performed, we have the post-production. So we have the union of the point cloud, and the point cloud is imported inside the software, the modeling software, in this case, Autodesk Revit. And then a core file is created in order to model the different disciplines. Which discipline we have in this case? We had structural, divided in concrete and steel. We have landscape, and we have temporary works. I mean, all the site structures, because as I said before, this is an unfinished work, so it's still a site, and also map. But how do we model this kind of structure you can imagine this is a very complex shape. So we use the computational design, and we use Dynamo, which is a computational design software, for the definition of the geometric references and how these references were born with spatial coordinates coming from the executive projects. Okay, in this case, we have a base and we, Dynamo takes rows and nodes, and then we assign structural families. In this case, we have a base to start this kind of modeling, and overlapping this structure with the point cloud, we were able to update the position and also the elements. Then so we have the modeling of all the structure, the single discipline. So overlapping, as I said before, the point cloud with the model, we were able to model the whole structure. And of course, we have some steps of validation, and at the end, we are able to make the federate final IFC model. We don't have to forget the verification and checking. This is essential because a model needs to be readable by the platform, as I said before. So we have to do the BIM validation. We have to do the code checking, so the check of all the information that I have inside, and also that the infrastructure owner asks to us, and also the clash detection that simply are the overlapping of different models, and we can check all the interferences. But in this case, because this is such a complex structure, another kind of check was done. So the comparison between the IFC model and the point cloud in order to detect some gaps that we have with the modeling. This kind of check was done with the software Leica 3D Air, and as you can see here, we have the green color when there is no gap between the model and the point cloud. In this case, we have a total control of the modeling that was carried out. Here, we can see the complete IFC model. We can see the topography that was made with the survey was made with the drone. We have the map here, because here we have all the underground sewage system. And here we have the concrete structure and the steel structure. Here can we see some other point of views of the model. This is inside the sail. And here you can see the high level of details that was reached. So on the left side, you can see the model, and on the right side, you can see a real photograph. So you can see the detail that was reached, for example, on all the structural elements such as tubulars, blades, and bolts. Of course, we used the point cloud, but also we use the documentation, because you can imagine that it's not possible to understand which is, for example, the thickness of an element. So we use also the documentation from the executive design project. Here we have a screenshot of the IFC model. So here we have a plate, and we have all the information that we have inside. In this case, the owner asked us to detect also the state of degradation. So some structural investigations were performed on the cover steel, and everything is inside the BIM model. All this information are also in the map model. As you can see, we have, as I said before, we have the sewage system that was modeled with the as-built that we received from the company, and also some verification on site. Everything in BIM and everything with all the information inside it. And to conclude, we want to show you a tour of the model. As you can see here, we are on the top of the structure, and we can see all the unfinished elements, for example, the starter bars and also the scaffoldings that we have inside. Here we are seeing the swimming hall, because this project was divided in the swimming hall and the sports hall. As you can see, we can see how the detail of the elements of the structure. To make this model, it took almost 10 BIM specialists and almost 6 months of work, with all the verification that the owner of the structure made.
That's why it's not for free, right? We at the end.
And then we go in the bottom side, that we have a detail of the concrete part. You can see the complexity of this structure, and also you can see that each element is different from another. Now we are entering in the sports hall, and since this structure is supposed to be symmetrical, also another steel cover supposed to be built, but as I said before, it was never finished. So we hope you enjoy, and if you have any questions, please. Thank you.
You have a question on that?
For the state of decay of the building?
I'm sorry?
Regarding the state of decay of the building, does the BIM model predict like when the decay will get to like a critical point, failure or something? Is it decided?
It depends on the information that you provide in the platform. But of course, you can predict the status in the future, and this is the use of the platform that we have. This means provide information inside the platform helps you to understand which will be the future state of the buildings and to anticipate the maintenance activity that you will perform in order to maintain a good status. If you want to maintain a good status, in this case, maybe you can also understand which will be the cost that you need to put inside the infrastructure just to complete it. And that's why the manual asked us for this kind of investigation. So Rosaria was really detailed, so you don't need any other question. Okay, thank you.
If you want to ask, I don't know, later, you can find my email, so feel free to ask questions. So in the future.
It's not for free then.
Thank you, everyone.
So thank you all to participate, and see you for the one interested on the 14th for the next event. Climate resilience. Bye bye.